So enough said, but I'm happy to be back and happy to be talking on my continuing evolution with Bayesian networks and how it's influenced my work over the past few years and some of the things that I've been up to most recently. For those of you who don't, oh, I do have a video. Look at that. For those of you who don't know me, I'm a wildlife biologist. And I work in Western Canada and mostly on big animals. That's why I always have the good pictures. And so we collect data in a variety of different ways. The main thing, one of the main purposes, of course, is to understand how animals are using their environment. And so we do that sometimes with wildlife cameras. So we have these remotely triggered wildlife cameras. Those are examples here on the right where you just kind of strap them to trees. You put up a big grid, put one every kilometer or so on wildlife trails or old road beds or whatever. And then you just wait till animals walk in front of them. They take a nice picture. And then you can index the use of different areas by different species. And then the other way we do it, of course, is with telemetry data. So this is an example. I hope the video plays okay for you. This is an example of them capturing um, caribou, in this case, in northern British Columbia. You can see that it works pretty well. They don't actually have to tranquilize the animals. That was someone with a net gun. They just push over the animals, catch them in a net. And then you can see the other animals that are nearby aren't particularly bothered. They just kind of stand around and watch while the researchers process the animals. They take a bunch of blood tests, etc., and then they put a radio collar on the animal, and then release it to get back to its buddies. And you gotta be careful when you're unhobbling them and taking the mask off just to keep those antlers away. These are females. They have little antlers. Both the males and females have antlers, but the females have much smaller antlers. You can see very clearly the radio collar on there. Weighs about 500 or 600 grams. Sends a location to a satellite once or twice a day, and so we get very accurate GPS coordinates on where animals are hanging out, and that those collars last for 3 or 4 years, depending if you're getting fixed rates every a couple of days, and so you can get some fairly significant data. But you can see there is some stress to the animal, but it's pretty minor. You can see she's kind of thinking, what just happened to me? But she's out with her buddies, and so everything's okay. So obviously, these days, a radio collar costs $2,500 or $3,000 or so, and of course, the deployment costs are even higher because you've got to hire a helicopter, very specialized work. So we try to do things with wildlife cameras as much as possible, but it's not the same kind of data. Um, okay, I wanted to stick these pictures in just because I don't know if you've been hearing, but we've been having some wildfires in Canada. So we occasionally get a letter from a cranky American governor in North Dakota or something, complaining that we're spoiling his barbecue season. We try not to. It's not something we're really happy about. But anyway, I've been doing a lot of work in the province of Saskatchewan recently, and I'm sure that's a place you've probably heard of, but I never really thought about. But it's kind of right smack dab in the middle of the country, kind of prairie farmland in the south, but more of this boreal forest in the center of the province, and that's where I've been working. And it's subject to some pretty significant fires last year. This is just a series of three photos here, and you can see it's kind of interesting. So this one on the left, there's a little black bear walking along this path. And this center photo, you just see some smoke starting back in here, just a little bit of grayness. And then the time difference between this middle photo and the photo on the right is 3 hours. No, sorry, it's not 3 hours. It's 45 minutes. 45 minutes between the second photo and the third photo. And so you can see how rapidly these fires move through these areas. And so the temperature here captured on the camera is 27 degrees on this center, 27 degrees Celsius. And on the right hand, it's 42 degrees Celsius. So a huge change in 45 minutes as these fires sweep through. And of course, that's one of the things that we're trying to understand the effects of, are how these kinds of natural events, but also man-made events, human-made events affect wildlife habitat. So lots of things obviously happen in Canada on the land base in terms of a resource economy. So be it extensive logging, like this picture on the right from Vancouver Island, to coal mining, a lot of coal mining in northern BC. For instance, that's a lot of coal we still mine a lot of coal for metallurgical purposes. So you need for steel making, basically, a lot of coal still gets mined. And then for things like oil and gas, like I'm showing down on the left-hand side, this is a platform in a remote area for an oil platform that's operating. And the way we study this in general is we take our telemetry points. So you can see on this photo all of these red points, which are telemetry dots. And what we're doing is we're querying a bunch of map layers in a GIS to describe what the habitat is like at the particular areas that those points were found. And so this can be all kinds of different data. Most importantly, things like habitat type. In this particular situation, I've got age of forested cut blocks, so 10, 20, 30, 40 years old in these little green areas. And then I've buffered those areas by 500 meters. Those are these orange things, and also all the roads, because animals tend to stay away from roads. So we want to know whether or not they're within a road buffer or not. And then also in this case, fires, which are these purple areas here, in this case from 1972 to 2010, because I was studying the vintage of data at that point. And so we take all this information, all these various habitat layers, and we want to relate those habitat layers all to the points. And of course, this is just like, even though we all come from different disciplines, we're all kind of doing the same thing, which is to say, okay, how do these various predictors explain the use of caribou, in this case in central Saskatchewan? How does it explain how what aspects of the environment are caribou selecting for? What aspects are they avoiding? And that's, of course, so that we know what the effect of these various either man-made or anthropogenic stressors are, with the goal, of course, of revising our practices or restoring habitat or whatever it is we want to do to try to put things back in a condition which they find suitable. And so we have our own workflow for this, statistical workflow, parametric workflow, um, and really, this has really become cookie cutter stuff, and it has been driving me crazy for years. And I was at a conference probably 3 weeks ago, and I probably saw 30 talks that followed this exact recipe. And yeah, it gets a little tiresome. But basically, what we do is we take all those what we call the used points. So every time we have those red dots, that's all the points that are being. We consider those the areas that are being used by the caribou, first of all. And then we have an equal number of available points, and we're comparing those used points to the available points. So it's kind of a binary setup. So we're using a logit link in our generalized linear mixed models. Um, we have several of these predictor variables: habitat type, time since fire, blah, blah, blah. And generally, they get grouped in what are called ecologically plausible candidate models. So you don't want to test everything, but you want to test some subset. But sometimes people test every possible combination as well anyway. And then there's things that we have to do to meet the requirements of these tests of the parametric test. So, they don't deal with categorical variables very well. So you have to code all your categorical variables as dummy variables against a reference state, screen for multicollinearity amongst your predictors, and throw at the ones that are highly correlated. Include individuals as random variables. So this is an important point because we're collecting a lot of points, but on a few animals, right? So it's kind of a nested design. So we might have 20, 30, 100 animals with radio collars on them, but we might have thousands of points within each of those animals. So the way to deal with that is that's why it's a mixed model, obviously. You fit the model of the data and then usually calculate some information theoretic score, almost always AIC, Icke's information criterion. Assume any model that's less than 2 AIC from the top to have ecological support. And then we carry on as if uh, you know we've made some great causal discovery, even though we've only done a correlational a correlational study. Um, and sometimes this is taken to extremes. So this is an example of a table from a paper with all the candidate models. This is from a study on Rocky Mountain elk, 38 models that they tested in this. They had 6 models that they considered to have support, but of course there were all these different combinations of the variables. And I don't know what you make of this. It's just this big mess. And obviously this is if you've been hanging around Bayesian networks and the discussions of causal Bayesian networks and Judith Pearl's work, this is not news. It always is when I bring it up and start complaining about it in these conferences because everybody thinks, well, this is just the way you do it, and what other way could we possibly do it? Blah blah blah. And there's lots of critiques that have been described, and I think one of my favorite ways of characterizing it this that I came across is something called causal salad. So this came from somewhere in the social sciences. This guy Richard McElreath, he's got a good YouTube video up, and if you're into this stuff, you'll just nod along. It's all pretty standard stuff, but I kind of like this idea that you kind of throw all of your predictors in the bucket, and you toss until the ones that are important kind of float to the top. And so and that's not the only issue, of course. The other things that really kind of bother me about this technique is it's a used versus available. It's not used versus unused, right? Because we know the kind of the units that the animals are using, and we're comparing them to what's available, but we don't know. But in some cases, they will have used some of those available units. So it's not really binary, but we're using a logistic test. So it's not really it actually doesn't fit the statistical model very well because there's some pollution of these available sites with used sites basically. And then this idea of screening for collinearity, you're kicking out variables that are highly correlated, but you have to choose which ones to kick out, of course. And you also see people kind of avoiding categorical variables because they're kind of difficult to interpret when you have to code for them and you have to think of it in terms of this reference variable. It's all very messy. And so you find that, at least I find, that people are actually doing some kind of fine tuning, kind of pre-tune their models to meet the statistical assumptions of the tests. So we're kind of messing with stuff just to meet the requirements of the test rather than um, trying to stay true to to the ecological approach, right? So for years, I've been trying to move this whole workflow into more of a Bayesian framework. Um, and I presented on some of that stuff in the past. And obviously, the first thing to do is that you just kind of replicate that kind of study where you have a series of predictors and you learn the structure, and then you parameterize that, and then and just doing that actually ends up kind of solving a lot of these problems, right? So um, just by replicating this in just a kind of straight up Bayesian network. First of all, it kind of gets around this problem of use versus availability and the fact that it's not really binary, and so the logistic doesn't really fit. But you can actually model this directly, right? So your target variable can be use versus availability. It doesn't have to be. You don't have to assume use versus unused necessarily. You can kind of do that directly. Obviously, we're seamlessly accommodating categorical variables. We're natively modeling nonlinear effects. I didn't even mention that, of course. That's one of the major assumptions of a linear model, obviously. And you don't have to concern yourself so much with this tuning for this multi-collinearity issue, because you don't have to, yeah, you can handle that quite well. So these are all advantages, but and of course you can still kind of generate a table and list your relationships between those variables, understand the relative effects of all these different variables in your system. So that all works very well. Um, and I've used that to good effect, I'd say, in a number of papers over the years. I've presented on these in the past. I've used it for mountain goats. I've used it for caribou. I was hoping this year to present on bison because I was getting cranked on a bison project in northern Alberta. There's still bison there, believe it or not, like free range roaming bison. But yeah, we haven't quite got that one off the ground. So maybe in a future year, I hope. But when it comes down to it, it's all still causal salad, right? So, and I went back and forth on whether I really needed to move to a more causal framework. Because I thought, well, going back to the standard question. So am I developing my models for prediction or for explanation? And I mean, maybe I'm just kind of characterizing the habitat they're using by these animals. Maybe that's okay. Maybe that's enough, right? Maybe I can leave this. I can learn these models, and I don't have to kind of make them causal. And then I thought, well, no, that's not really true because what we want to do, of course, is intervene on these systems to try to make things better for the animal. And those interventions, those are treatments. And so we want to know the potential effect of some of these treatments. So, um, if I mean, should we put out the fire or try to put out the fire? We're not very good at it, right? But that's kind of an intervention. And so I thought, okay, let's make this causal. And so the remainder of my slides here are just kind of the things that I've been coming through in turning these models into a more causal framework and things that I've been thinking about and hopefully provide some guidance to those. I know we've had lots of talk about causal models in this, and so maybe other people have thought about some of this stuff and or maybe they haven't. So, or if you're talking about moving to a more causal framework, because I've also heard that over the last couple of days as well. And the first thing, of course, is that you need to be deliberate in your design. And so that means just don't take your naive Bayes network and reverse the arrows, right? There's more to it than that, obviously. These are really, you're encoding your causal assumptions and you have to be able to defend those. And so it's really important to think about how that works in your particular system. A couple of interesting things that I captured in this particular case. Obviously, this is my location, so this is my used versus available contrast here. And yes, I have these predictors around what what the ecosystem looks like, the time since we've had wildfire, this anthropogenic buffer, that orange piece that I was showing you, and the time since those areas have been harvested. Those are all effective, but of course, there's other things that are selective on the environment on the landscape. So fires, for instance, not everything burns in the same way. So different ecosystems burn in different ways. If you're in a wetter ecosystem, it's less likely to burn. So fires are selective as well on the land base. And as it turns out, so are forestry companies. So um, forestry only goes where the wood is most productive, and they tend to leave the least productive wood, obviously for obvious reasons. But they tend to be, so it turns out that they're extremely selective on the environment. In fact, they're more selective than the caribou are about where they're actually putting their operations. So those are important correlates to capture, or important causes to capture in this kind of structure. The second thing is just thinking deeply about what a cause is. Like, what is a cause? Because not all causes are equal or obvious, and so there's a certain camp that says, no causation without manipulation, basically. And that makes sense. So if you're a social scientist and you're studying, say, the effect of income support on, and I don't know, help education outcomes for children or something like that. Um, then yeah, you can manipulate income support. That's the intervention. That's the treatment that you're interested in. So it makes sense to vary that. You can vary that, and then you can determine its cause. Um, but another but if you go down that road, then you'd say, well, what about, say, sex? You can't change you can't manipulate sex, although that's more controversial than it used to be now, I guess, at least amongst humans. I don't have to deal with that. We don't talk about transgender moose, so it's okay. So but yeah, it's different. But so some people would say, well, you can't treat sex as a cause because you can't manipulate it. But at the same time, well, that doesn't make any sense, because what if you're studying something like discrimination in the workplace? You say, well, of course discrimination is caused by sex. So you're not going to say that sex is a cause of discrimination because you can't manipulate sex. No, that doesn't make any difference. So if you kind of take Ude's Pearl's approach on this, that you don't want to restrict causation to just those things that are humanly feasible actions. You want to define that more broadly, and so it could be theoretically manipulable. So that's the way I kind of think about it. Um, but you still get into these kinds of weird situations, and the test that I kind of come up with is, well, does it make sense as a direct effect? So I can see how, say, male and female animals will use habitats differently for different reasons that are independent of the other variables that I'm measuring. So as a direct effect, it makes sense. But if I think about something like season, season is certainly a cause of how animals are using their habitats, but it doesn't make sense to isolate that as a direct effect independently of everything else. So it really is a variable that kind of affects how other variables are interacting, but doesn't make any sense to deal with it on its own. And so sometimes we call those effect modifiers. Of course, you can deal with this all in the design of your DAG, and that's great. But you end up kind of with this mix. You have kind of causes that you can control, causes that are still causes, but that you can't control. And then you've got these things. Season is still a cause here, but doesn't make sense as an effect, except in relation to other things in your deck. So you got to kind of keep these three things in your head and be able to kind of make your audience and decision makers, et cetera, kind of understand the distinction before people get caught in this idea. Well, you can't just change, wetlands into uplands or something. That doesn't work. So why are you even talking about that as a cause? So that needs to be worked through. Um, the other thing is around measuring causal effects, and I'm going to say up front, like BayesiaLab automates a lot of this stuff, right? So I'm doing this kind of from first principles, but obviously with the software tools, with very powerful software tools, you can automate a lot of this stuff. But even when you do a causal network, it's still kind of tempting to just read off the mutual information or something similar, your Kale divergence, and say, that's how I'm measuring the various impact of these variables. But when you're interested in causal effects, you want to say, okay, how much does intervening on this variable change the distribution of the target? And you want to run through that for all the states and all your variables. And that's what's known as average causal effects. So what's the effect of doing that treatment minus, oh, I forgot the minus on that top one. Yeah, minus the effect of not doing the treatment, right? And so the difference between those is your average causal effect. And this top equation is if you have a binary case, and then the bottom is if you have more than two states in your node. So in that case, it's what if you do the intervention compared to if you just have if to no intervention where you just have the priors for that particular node. And so these measures are then, and it's kind of basically like clicking through everything on every possible combination on your Bayesian network, although making sure that you're doing the appropriate graph surgery, obviously, like in BayesiaLab, setting as an intervention rather than an observation to make sure you're reading that off, and then you can map that out. And so one of the effective ways, because I'm always trying to think of, okay, how do I get my audience that are used to GLMs? How do I make sure that they are following along and they understand this? And they use a lot of these so-called lollipop graphs, right, where they would map all of the beta coefficients kind of from the most positive to the most negative with a line at zero, saying, okay, well, all these things tend to be selected by animals if they're to the right of the line, and they're being avoided by animals if they're to the left. And so I can align these things in the same way that is familiar to them. Um, but this actually kind of takes it one step farther, because rather than just having all of these arranged by all of the habitat or all the different variables, this is actually states within variables. So it can actually move back and forth. So in this case, the top one is around a certain ecosystem, this black spruce tamarack bog fen. They really like that. So that's highly selected. But the next thing is around this anthropogenic buffer. The second most important thing is that they stay out of that anthropogenic buffer. But then the third thing is actually on back to a ecosystem around a pine lichen. So they like that pine lichen almost as much as they like staying out of an anthropogenic buffer. But I'm switching back and forth between the variables and aligning these states as well. But at the same time, we also want to see um, what the kind of predictor level is. And Again, you can get that in BayesiaLab when you start getting into the direct effects measures, et cetera. But there's different ways of measuring that too. So if you think, okay, so what does it mean to have a high average causal effect in the case of say of different ecosystems? And so you could, or if you had different states within a node, you could say, well, the effect of that node, that the effect of that variable is equal to the strongest effect of any one of those states. Or you could say, well, it's the difference between the state that has the biggest impact minus the state that has the smallest impact. Or you could say it's the average of all the states or the standard deviation of all the states. So there's different ways you could measure that. And and you have to think about the circumstances in which you're working and which one of those measures actually makes sense. Random effects. So I just wanted to close on this. So this is one that I haven't quite cracked here. So as I said, we have a few animals with lots of locations within animals, and this has come up. So we had Bezos talk yesterday, which I found very interesting. Same kind of thing. She was looking at children within clinics, right? So it's a multi-level or hierarchical Bayesian network. I think that's where I'd have to go. There's a couple of ways to, few ways that you can also do this. Like you can include individual as an ID, as a node. The problem with that, of course, is you end up with you end up very sparse CPTs. Like that's the other thing when you and I didn't mention this, but I know that Lionel was asking in Steve Fraser's talk yesterday, that um, you got a lot of arrows pointing at your target node, and so you got to be really careful that you don't end up with a sparse CPT. So obviously, I was adding an individual as a node that would blow up the size of that CPT. So yeah, I need to do more work on that hierarchical side and try to figure that out and see if I can code that. I don't know how to do it. So I have to look at Bayesia's talk yesterday a little bit more closely. And then finally, the other way you can do it, which is not very satisfying, is you basically include a latent variable and you give it some states, and then you learn your network, and then see if that latent variable is significantly influencing the network, and then you say, and you interpret that as individual effects. But that's an assumption, right? And so I've done that. I haven't really liked it, but that's one approach. So those are some of the lessons. I hope that's helpful as I continue to work through on this kind of causal journey. I just wanted to finish with a few more photos of that fire from Saskatchewan, because it really is fascinating when you get these camera images. And a lot of them you just have, oh, here comes here comes the fire, and then there would be not, then that would be the end because the camera burned up. But again, so the first you can see actually some flames starting to show up here, and then these first four photos again occur over the span of 3 hours. So the fire is kind of distance at a distance, comes closer, and is basically burned through in 3 hours, just gone. That's it. But then a little bit later, about 3 days later, with the ground still smoldering, the moose are back. And so, yeah, we don't have to worry too much about these animals. They have evolved in a landscape that is used to lots of fire. That's historically these forests probably burned every 80 years, and that's where those animals evolved. So they get it. Obviously, global warming is increasing the frequency and intensity of those fires, which you have to worry about. But in general, the animals are doing just fine. So I'll stop there. If there's any time for questions, I'd be happy to answer them or try to answer them, Stefan.